Hey there. So, this next chapter that we are getting into is basically all about the applications of derivatives. Um, Chapter 2 is all about how do we find derivatives with product rule, chain rule, all that stuff. And then this chapter really gets into the idea of graphs. This is really graph heavy, and we're going to be relating, the graph of f with f prime and f double prime and all that stuff. But we're going to be doing a lot of derivative work within all of our problems. So this first section is all about extrema on an interval. And there's going to be a couple different types that you can be asked about that we're going to get into. But this lesson is all about absolute extrema. How do we find the absolute extrema on an interval? And what that means is, how do we find the biggest y value and how do we find the smallest y value on an interval if we don't have a graph? So I have some graphs depicted here, and it says examine, and it says determine the maximum and minimum of each graph if they exist. Now, when a question ever says what is the maximum or what is the minimum, they are looking for the y value of the function, like the biggest y value or smallest y value. Sometimes they'll say at what x value does the maximum occur? And so we always have to pay attention to what the question's asking. So if I look at this graph, if let's say these are just all named f, these are all f of x, then I would say the maximum of this, the biggest y value, is f of c. So that is the max, and that occurs, it doesn't ask, but it occurs at x equals c. So just having you see the difference between what the max is versus where it occurs. The minimum is this lowest y value right here, which would be f of b at x equals b. And then we go to the next one, and it says, what's the maximum here? Well, it's pretty obvious. The highest y value is right here, again, at f of c. Now if we talk about the minimum, now I want the smallest y value on this function, and this is where things get a little interesting. It would normally be right here if that was a closed circle, but as we can keep getting lower and lower and lower on this function, right? We can never actually approach that open circle, so there actually is no minimum value of this function, because if you give me a y value that is pretty low right here, you can always get one even lower. And so we can never actually get to that open circle. There is no minimum value. Does not exist. And we'll talk about why that's important here in a second. And if I want the maximum value of this, well, again, I can keep going higher and higher and higher towards that open circle, so there actually is no maximum value. The minimum value is pretty obvious, though. It's f of b. What this does, this leads to our next theorem, okay? Our next theorem is called the extreme value theorem. We already have a couple of theorems we've talked about. We've talked about the squeeze theorem, and we've talked about the intermediate value theorem, and here's our next one. And we don't have very many more. So the extreme value theorem says this. If f of x is continuous, so we need a continuous function, on a closed interval, remember, closed interval means the endpoints are included. So these are our conditions. All we need is a continuous function on a closed interval. If you have this, then the function has both a maximum and minimum on the interval. So if a function is continuous on a closed interval, endpoints included, then f of x will guarantee to have a maximum and minimum on the interval. And it's kind of like what the intermediate value theorem was, where it doesn't find anything for you. It just tells you if these conditions are met, then this will happen. And so if we have a continuous function on a closed interval, we will have a highest y value and smallest y value. Kind of a duh theorem, but they'll ask about it. Okay, the next part here is critical numbers. Now, they sound pretty important. The word critical is in there, and I will say they are very, very important because pretty much all the problems we'll tackle in these first few sections of this chapter all revolve around critical numbers. Like, these are going to be the first things we have to find in pretty much every problem. They are that important. What critical numbers are, first of all, they are x values. Critical numbers are x values in an interval. X values in an interval where the derivative equals 0 or undefined. So they are x values in an interval that make your derivative 0 or undefined. Really, it's finding any weirdness on your function, any horizontal tangents, any sharp turns, any vertical tangents. These are numbers where anything kind of weird happens on your function. That's what critical numbers are. One really important thing, I would star this, critical numbers must be in the domain of the function. Critical numbers must be in the domain of the function. Basically what that means is they have to be x values that are on the function to begin with, that are located on the function. So they have to be in the domain. So real quick example here. If the question said, find the critical numbers of 3x squared plus 6x, that would be the question. They give you this function and they say, find any critical numbers of this function. Well, anytime we're finding critical numbers, we start by finding the derivative. So 6x plus 6. And then anything that makes this derivative 0 or undefined are critical numbers. And the only time you're really going to have undefined is when you have a fraction, anything that makes the denominator 0. Since we don't have that here, then I would just set this equal to 0, and I would find that x equals -1 is a critical number. So -1 is a critical number of this function. Pretty much that means on this function at -1, there's going to be a horizontal tangent or something weird going on. Obviously, it's going to be a horizontal tangent because this is a parabola. But it could be where sharp turns occur and things like that. Okay. So as I said, we are going to deal with two different types of extrema throughout this chapter and throughout this course, to be honest. The first type is going to be absolute max or mins, and this is what this lesson is going to be all about, is how do we find the absolute max or the absolute min in an interval, the highest y value or smallest y value in an interval. That's what this lesson's all about. We will get into, but not really today, we will get into what's called relative max or mins. And so I'm going to talk about that first just because this is not really what today's lesson is about. Sometimes these are called local max or mins, but these are going to occur in an open interval They're going to occur in an open interval. What that means is not at endpoints. Relative max and mins will not occur at endpoints of an interval. So they'll occur inside an open interval at hills or valleys. And I'll talk more about that here in a second. You can have more than one relative max or min. Something else to point out, these occur at critical numbers. Another thing to point out, not at endpoints. And the last thing to point out about relative max and mins is that not every critical number is a relative max or min. We'll spend a lot of our time in this chapter finding relative max or mins, but like I said, today is all about absolute max or mins. So absolute max or mins, These occur at critical numbers. They can occur at critical numbers, or they can occur at endpoints. So that's the big difference between absolute and relative. Relative will never be at endpoints of your function. Absolute max or mins could. Okay. So let's kind of talk about the difference between absolute and relative with this function right here, and then we'll talk about how do we find absolute extrema. We'll do a couple different examples. So if I look here and it says, what's the absolute maximum? The question is, what's the biggest y value that we see of this function? And it's right up here at this peak right here. So in this case, it would be f of d. That is the biggest y value of this function. The absolute min is the smallest. It's kind of hard to tell. It looks like this little valley right here and this endpoint are pretty similar. A is actually below, and so f of a would be the absolute min. Now, in terms of relative maximums, okay, relative maximums are if you would hone in on any certain point of this function, any certain, I should say, subinterval, is there a highest point? And so it's really going to be at any sort of hill, any sort of highest point. Like right here, you can kind of see in this little subgroup right here, f of b, I should say, is the highest y value there. F of b is considered a relative maximum, along with f of d. So any highest point that you notice inside of an interval is a relative max. So f of b and f of d would be considered relative maximums. Notice that the derivative here would be 0, so a critical number. The derivative here would not exist because you have a sharp turn right there, so a critical number. So notice that we have two different relative maxes. One occurs when the derivative is 0. One occurs when the derivative does not exist or is undefined. So, talking about critical numbers there. Relative mins, well, those are going to occur at little valleys. So right here, f of c and f of e. I mentioned up here, not every critical number gives a relative max or min. To show you an example of that, if I had a function, let's say x cubed function, like this. Well, right here in the middle, the derivative would be 0. It has a horizontal tangent right there, but you could tell that this is not the highest point or lowest point in any subinterval of this function. So this would be a critical number right here, but this would not be a relative max or min. So relative extrema have to occur at critical numbers, but not every critical number will give a relative max or min. Again, we'll talk a whole lot more about that in upcoming lessons. Today's lesson is how do we find absolute extrema on a closed interval? How do we locate it? Okay, so here's our process, kind of a 4-step process. Step 1, find the critical numbers. In the open interval. Find the critical numbers. What that means is find anywhere f prime equals 0 or undefined. So we have to identify what the critical numbers are. That'll be step 1. Step 2, find f of x at each critical number. Basically, plug in those critical numbers to your function and get your y values. You're actually finding the y values of this function at the critical numbers. Well, the other place that absolute extrema can occur are at endpoints of the function. So then we have to test the endpoints. And this is kind of the thing that as the year goes on, students forget about most often, is plugging the endpoints into the function. So we have to find f of x at each endpoint. So really what's happened here is the absolute extrema have to occur at critical numbers or endpoints. We find the critical numbers, we find the endpoints, plug them into the function, and then we just see, step 4, what's the biggest and what's the smallest y value. Identify the least and greatest y value. Find your critical numbers, plug those and the endpoints into your function, and just see with your eyes what's the biggest and what's the smallest. All right, let's do a couple examples. So locate the absolute extrema of this function on -1 to 2. Well, following our procedure, we first have to find critical numbers. So I have to find f prime. So 6x. And then I need to find where does this derivative equal 0 or undefined. Well, obviously that's going to be at 0. 0 makes this 0. So that's our only critical number right there. 0 is a critical number. So the last thing we need to do is plug in our critical number and endpoints into this function and just analyze our numbers. So now I'm after f of -1, f of 0, and f of 2. So I'm trying to find the actual y values on the function. So notice I'm plugging these into f, not f prime. So when I do that, when I plug -1 into f, we get -1 out. When I plug 0 in, we get -4 out. And when we plug 2 in, we get 8. Now I just identify with my eyes, the smallest and biggest. So we have our min right here, and we have our max as 8. And so I'm going to write that out. I'm going to say the max is 8. So if they ask what is it, it's 8. If they would say where does it occur, I would say at x equals 2. I would say the min is -4 at x equals 0. That's our procedure. Let's do a couple more. You could pause and try this one if you want to here. That's up to you. It's always good to try things out. So we are going to find the absolute extrema on -3 to 0. First thing, find critical numbers. When in doubt, find critical numbers. That's a really good practice. So we're going to have 4x cubed minus 32. Okay, I'm trying to figure out where does this equal 0 or undefined. The undefined, I think, will show up in your homework. You'll have some fractions to deal with. Let's solve this. So add 32, divide by 4. So 8 equals x cubed. Cube root both sides. X equals 2. That's our critical number. But notice, 2, here's where you need to be careful if you tried this one on your own. 2 is not in the interval. So 2 is kind of irrelevant for this whole problem. The absolute extrema it can't occur at 2 because 2 isn't even in the interval here. So which means throw it out. So to find it, all we need to analyze is what is f of -3 and what's f of 0. We're just thinking about the endpoints now. So f of -3, if I plug it in, would be 177. F of 0 is 0. So the max is 177 at x equals -3. The min is 0 at x equals 0. All right. Last one. Find the global. So global and absolute mean the same thing. They've moved towards using the word absolute, but you could see global show up. Of the cube root of x from -1 to 1. Step 1, find our critical numbers. So this is just x to the 1/3. So it'd be 1/3 x to the -2/3, which is really 1 over 3x to the 2/3. And so at this point, this is our first fraction we're dealing with. Your critical numbers are really whatever make the top of your fraction 0 and whatever make the bottom of your fraction 0. So nothing makes the top 0, but 0 makes the bottom 0. 0 makes this undefined. So x equals 0. I always check, is it in the domain of the original function? That's something always good to check. It is, so 0 is a critical number. That's something to pay attention to. So now I have to analyze h at 0, -1, and 1. H of 0 is 0. H of -1, cube root of -1 is -1. And the cube root of 1 is 1. And then I just look for the smallest and biggest. So the min is -1. at x equals -1. The max is 1 at x equals 1. That's your procedure. You find your critical numbers, plug them in, and the endpoints, and just analyze. The next one gets pretty hairy. I'll put the answer key up if it's something you want to look through. It might be something we deal with as the chapter moves on, but I didn't want to spend a ton of your time. I mean, you can kind of see it right here. Just a lot of unit circle stuff. I'm not saying you won't have to do this stuff. I'm just saying I didn't want to go through all this right now and take up your time watching a YouTube video on it. But it's the same procedure. You find your derivative, chain rule right here. Set it equal to 0. There's some factoring involved to get your critical numbers. This takes you back to pre-cal. And then you just analyze f at all these values and endpoints. So again, just a lot of unit circle stuff. So if you want to, look through that and make sure you understand it, probably good practice. But for now, you have an assignment, and let me know if you have any questions at all.